Double pulse testing is widely used to measure the performance of half-bridge switches. I'm going to show you how to perform a double pulse test to determine energy losses in the switching devices on this Wolfspeed silicon carbide evaluation board. I'm using a 5 series MSO oscilloscope with the wide bandgap analysis package, available as option WBG-DPT. In this demonstration, I'll show the energy loss measurement, but timing measurements and reverse recovery measurements are also available in the wide bandgap analysis package. In addition to the 5 series MSO, the package also runs on the 4 and 6 series MSOs. Energy loss measurements work by multiplying the voltage across and the current through a FET to measure power. The power is then integrated to find the energy. Since 2 separate probes are used to measure those parameters, it's absolutely critical to accurately time align the measurements. Before testing, it's important to de-skew the setup. I used a splitter and pulses from the AFG 31000 signal source to de-skew the probes and the CVR cable. With the probes de-skewed and warmed up, power to the DUT turned off, I'll run a quick auto zero. This will remove any imbalance that will affect switching loss measurements. I'm using the AFG 31000 arbitrary function generator with the built-in double pulse test app as a gate drive stimulus. You can configure the DPT app on the AFG 31000 to fit your test requirements. For this DUT, I've configured the number of pulses to 2. I've set the first pulse width to 3 microseconds and the second pulse width to 2 microseconds, with a gap of 5 microseconds in between. Okay, now we're ready to use the silicon carbide evaluation board. This half-bridge circuit can be used for double pulse testing, synchronous buck-boost converter, or asynchronous buck-boost converter. I'm using the double pulse test configuration, and I'm going to keep the operating voltages modest since I don't have high power safety equipment set up here. One cool thing about this Wolfspeed eval board is it uses a current viewing resistor to measure drain current. The CVR is a specialized shunt resistor, placed in series with the current flow, and allows us to use a simple 50 ohm cable to measure current via Ohm's law. A BNC cable on channel 1 is connected to the CVR to measure IDS. A TPP1000 10x passive probe on channel 6 is connected to measure VGS across the lower FET. And a TMDP0200 differential voltage probe on channel 3 is connected to VDS. 2 DC power supplies are connected to provide the rail voltage and to power the onboard gate driver. Let's talk more about the probes used for making double pulse tests on the low side MOSFET. A TPP0850 passive probe can be used for VDS measurements, but be careful not to use it on any floating measurements. For floating measurements, use a differential probe like a THTP or TMDP0200. For this setup, I'm using the TMDP0200 differential probe. In this setup, for VGS measurements, we are using a TPP1000 10x passive probe. As I noted before, for making the drain current measurement, I'm using a CVR connected to channel 1 with a 50 ohm BNC cable. Now I'll show you how to set up the measurements using the wide bandgap double pulse testing application. I'll set custom units on channel 1 to read current from the CVR. Tap Add Measurement and turn on both Eon and Eoff energy loss measurements. Specify the channels connected to VDS, the drain current, and VGS. Now, set the max VDS, max drain current, max VGS, and pulse width. Based on these values, you can use the Power Preset button to automatically set the vertical and horizontal scales, configure the trigger source, and arm the scope in single sequence mode. Now, the scope is waiting for a trigger. After checking my connections, I'll energize the circuit. Turn on the rail voltage, power up the gate driver, and then enable the gate drive signal. Let me turn off these power supplies and then we can look at the results. The scope acquires the double pulse waveforms and the E-on and E-off measurements show the results. This circuit has an E-on energy loss of 434 nanojoules during the turn-on switching event, and E-off energy loss of 792 nanojoules during the turn-off switching event. If you want to analyze multiple pulses, you can go to the measurement configuration and select multiple pulse from the pulse region dropdown. This will compute energy loss on both the initial turn-on pulse and the full current pulse. If you are doing a pulse train with more than just 2 pulses, this will show results on each switching event. In multiple pulse mode, you can navigate between the different results using these arrow buttons. For each region, annotation lines appear on the E-on and E-off power waveforms, showing where the results are being calculated. Add a results table to see measurement values for every pulse. The results table will show statistics based on all the pulses that are in the current record. The best way to save your results and work with colleagues is the session file. A session file stores all of the waveform data, settings, and a screenshot together. These can be recalled later for further analysis. I can also save a report to document my results. As I said earlier, energy loss measurements are just one type of measurement available with the wide bandgap double pulse testing application. It can also help automate switching measurements and reverse recovery measurements. The silicon carbide half-bridge circuit in this video is a building block for countless power conversion applications. From 3.3 kilovolt locomotive boost converters to electric vehicle traction drives and solar power inverters, the Tektronix wide bandgap double pulse testing solution on the 4, 5, and 6 series MSOs, combined with the AFG 31000, power supplies, and probes, can help you quickly understand and optimize your designs to power our electrified future.